Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing PWM techniques. What are PWM techniques? This is nothing but pulse width modulation technique. That is, firstly, this is basically applied to the inverters. What is the reason why we are actually applying for the inverters? Inverter, basically it is a power electronic device which converts DC input to AC output. And here, that output of the inverter may vary. See, output of the inverter need to be varied as per the load requirement. And whenever input DC is varied, in that case, output can also change. And this output voltage need to be maintained constant, and we need to take care of these voltage fluctuations. And for that purpose, in order to compensate this particular voltage, here we are actually making use of we are actually maintaining voltage by frequency constant. Voltage by frequency constant. This ratio output voltage to frequency is actually maintained constant, such that we can compensate the output voltage or load voltage variations. That is the idea behind. You know very well, these inverters will be used in AC drives. So thereby we need to take care of the output voltage variations, and in order to compensate that, we are actually going for V by F method. That is maintaining output voltage to frequency constant. And here, in order to obtain such in order to actually compensate this particular voltage variations, we are actually going for pulse width modulation techniques. And here there are various pulse width modulation techniques like single pulse width modulation technique, multiple pulse width modulation technique. We have sinusoidal pulse width modulation technique, as well as modified sinusoidal pulse width modulation technique, as well as phase displacement control. We have these 5 types of pulse width modulation techniques, and let us discuss all these 5 in detail. In the first place, we will be discussing single pulse width modulation technique. So here, base drive is actually, there is single pulse of output voltage during each half cycle. If you see here, there is a single pulse width in a particular half cycle, and in another half cycle there is another pulse width. There is single pulse width of output voltage during each half cycle, and width of this particular pulse width is 2D. If you observe, the width of the pulse width is 2D, and the RMS value of output voltage can be controlled by varying this particular pulse width. And here, if you see, there is a base drive which is actually provided for the transistor 1 and 2, and if you see, this is the base drive which is actually provided for the transistor 3 and 4. And you know very well, transistors are fully controllable devices. As long as we provide the base drive, that long that particular transistor will be remain in on position. And the moment we withdraw the base drive, that particular transistor will come into the off state. And here, thereby, since we are providing the triggering pulse for transistor 1 and 2, here the output voltage is present from this instant to this instant, and the width of this particular pulse width is 2D. And if you see how this actually, this pulse width is actually obtained, let us see that procedure in detail using these diagrams. And if you see, this is a carrier wave, this is a carrier wave, and this is a reference sine wave. And when these two particular waves are compared, in that case, our amplitude of the pulse width, it actually depends upon the amplitude of the reference wave. And if you see, when these two particular carrier wave as well as reference wave is compared, in that case, whenever this reference wave is actually striking the carrier wave, at that instant, a triggering pulse is generated. At that instant, we will have to draw a single line, and in the other instant, when this particular reference wave is actually striking the carrier wave, at that instant we get another pulse. And if you see, resultant of these two lines is nothing but our output voltage. and this is of pulse width 2D, and this is nothing but our output voltage of the inverter, and this is nothing but pulse width modulation technique. If you see, the carrier wave amplitude is denoted with AC, and the amplitude of the square wave, it is denoted with AR, and this is nothing but the resultant output voltage which is generated out of the comparison of this carrier wave as well as reference wave. And here modulation index is actually considered. And what is this modulation index? It is the ratio of amplitude of triangular wave to that of amplitude of square wave is nothing but modulation index, and it is given by the formula reference amplitude divided by carrier amplitude, and this is nothing but modulation index. And if you see, this particular pulse width can also be made near to that of the square waveform by making the value of the m is equal to 1. Alright, so width of the pulse can be changed by varying the modulation index by making m near to 1. In that case, almost square wave output is actually obtained. Hope you understood this concept. And this is single pulse width modulation technique. And this is that particular pulse width. By varying the pulse width, we can actually control the output voltage. But how this actual output voltage is actually obtained, in that case, we will have to verify this by the comparison of carrier wave as well as reference wave. The resultant output voltage will be generated. And later we'll see multiple pulse width modulation technique. And here, if you see, this is the carrier wave and this is the reference wave, DC reference wave. And here, these both waveforms are actually compared in multiple pulse width modulation technique. In that case, whenever this reference wave is actually striking the carrier wave, at that instant, we will get a single pulse. And later, when carrier is striking the reference, you'll get another pulse. When carrier is striking the reference, you'll get another pulse. And likewise, we will be getting the number of pulses. And these pulses are ANDed with the masking signal. This is one of the masking signal and this is another masking signal. And when these triggering pulses are generated after having compared with that of triangular and reference wave, these are the resultant pulses which have been generated, and these pulses are actually ANDed with the masking signal such that you will get the base drive required by the transistors which are actually present in the inverter. So here these two are ANDed and the resultant is nothing but the base drive of transistor 1 and 2. And these resultant pulses are actually ANDed with this masking signal, and the resultant are the base drive required for the transistor 2 and transistor 3 and 4. Okay, so if you take a full inverter, in that case, these are the triggering pulses for the transistor 1 and 2, and these are the triggering pulses for the transistor 3 and 4. So, when these are provided as a base drive for the respective transistors, at that instant, they will be triggered and thereby the resultant output voltage will be generated. And this is the output voltage of that particular inverter whenever it is triggered accordingly. And here, this is the negative wave, negative half cycle of the inverter, and this is the positive half cycle of the inverter, and this is nothing but the output voltage of the inverter. So here basically we are actually seeing the multiple pulse width modulation techniques where number of pulses are being generated. Okay, you may ask me a question, ma'am, how to vary the pulse width? If at all, if we need to increase the width of the pulse, in that case, we just have to increase the amplitude of this particular reference wave. Let us take this example. See here, there is a reference wave. What am I doing is, I am simply increasing the amplitude of the reference wave. When I am increasing the amplitude of the reference wave, see, this is the instant where it is striking the triangular wave such that the triggering pulses are generated in such a way that the amplitude of the triggering pulses which is now generated is wider when compared to that of the previous pulse which is being generated. Hope you understood the difference. By increasing the amplitude, the width of the pulses can be increased in the multiple pulse width modulation technique, and thereby modulation index will be varied. And if at all, if we can make this particular modulation index is equal to 1, we can nearly obtain square waveform. So that is the thing. And now coming to this particular V0 RMS value of this particular multiple pulse width modulation technique. So here V0 RMS, it is given by 1 by T, general formula 1 by T, 0 to T, Vs square of omega T, d omega T, whole to the power of 1 by 2. And see, if you see here, this is the pi by P, and this is the instant which is pi by P minus delta by 2, and this is the instant till where it is being conducted, that is given by pi by P plus delta 2. In that case, here a waveform is conducting right from P by P minus delta by 2 to that of pi by P plus delta by 2. And let us consider the same limits, and in that case here time period is, total time period is 2 pi. Every cycle, similar cycle is repeating for 2 pi, and it is actually conducting from, as we have seen earlier, pi by P minus delta by 2 till it is conducting till pi by P plus delta by 2, Vs square of omega T, d omega T, whole to the power of 1 by 2. And if we simplify this equation, we get Vs square, we are bringing constant out, Vs square by 2 pi, and here integration of 1 is, by substituting the limits, upper limit minus lower limit, we get pi by P plus delta by 2 minus P pi by P minus of minus plus delta by 2, upper limit minus lower limit, and this is whole to the power of 1 by 2, and this we get Vs square by 2 pi, pi by P minus pi by T gets cancelled, and we get this as 2 delta by 2 whole to the power of 1 by 2. In that case, we get 2 gets cancelled, and this is Vs root over delta by 2 pi. And in order to obtain the RMS value of the complete wave, let us multiply this with 2p. In that case, 2 gets cancelled, and we get Vs root over delta p by pi. And this is nothing but what? V0 RMS expression. And here distortion factor is reduced compared to single pulse width modulation technique. Here in multiple pulse width modulation technique, distortion will be reduced because the number of pulses are more. In that case, the output voltage waveform will be distortion free. And as the value of P increases, amplitude of lower harmonic reduced. So here, if you see in multiple pulse width modulation technique, the number of pulses are more. So here, with the increased number of pulses, switching losses also increases because depending upon the number of pulses, and these pulses will be going on triggering the transistors in a continuous fashion, thereby switching losses are actually increased. And apart from that, control scheme is also complex because we need to provide the base drives for so many times, and that is the only reason here control scheme is also complex. That is the thing associated with the multiple pulse width modulation technique. So in order to minimize all these disadvantages, we are now going for the sinusoidal PWM technique, sinusoidal pulse width modulation technique. So what exactly we are doing in sinusoidal pulse width modulation technique is, here we are taking the sine waveform, and this is nothing but the reference sine wave, and now this is actually compared with the carrier wave. This is compared with the carrier wave such that with the comparison of this sinusoidal waveform and carrier waveform, the resultant is the pulses which is being generated, and these pulses are nothing but it acts as a base drive for the inverters, base drive for the transistors in that of the inverters. So here, if you see, Vc is the amplitude of the carrier wave, and FC is nothing but the frequency of the carrier wave. And if you take the reference wave, and here reference is nothing but sinusoidal, whereas in previous cases it was a DC reference line, that was a straight line, whereas here it is sinusoidal waveform, and the voltage of this particular reference wave, it is denoted with PR, whereas frequency of this particular reference sine wave is FR. Alright, so now whenever this carrier wave is compared with a sinusoidal wave, when the sinusoidal wave is actually striking this carrier wave at these 2 points, let us draw a line over here, as well as this is the another line at which the sinusoidal is striking the carrier wave, and the resultant is nothing but the required sinusoidal pulse width modulation pulse which is being generated, and this will be acting as the pulse required by this will be acting as the base drive for the transistor 1 as well as for the transistor 2, which acts as the which is present in the inverter. So here again, when carrier wave is compared with the sinusoidal wave, when the sine is actually striking the carrier, at that instant we will get another pulse, and this is another pulse, and this is the third pulse which is generated due to comparison. And these pulses which are being generated will be acting as a base drive for the transistor 1 as well as transistor 2. Similarly, the other pulses which are being generated in the negative half cycle will be masked with the signals, and in this process the resultant pulses which are being generated are nothing but the base drive for the transistor 3 and 4. Hope you understood. Here in sinusoidal pulse width modulation technique, the sine wave is compared with the triangular wave, and when this sine wave is actually striking the carrier wave, the resultant pulses would be ANDed with the mass signal, and the pulses which are generated, these pulses are nothing but the base drive of transistor 1 and 2 as well as for the transistor 3 and 4 of the particular inverters, and those inverters will be triggered accordingly such that this is your output voltage of that particular inverter, pulse width modulated inverter, and width of the each pulse will be given by delta M. So here width of the pulses depends upon the amplitude of the sine wave. So here width of these pulses, as I already discussed in reference wave previously. See, if we can increase the amplitude of the sine wave, in that case the amplitude of the pulses which are being generated will be more wider when compared to that of the previous case. So that is the thing. By varying the amplitude of the sine wave, we can actually increase the pulse width of the pulses. And here, if the amplitude increases, width of the pulses increases, and modulation index is actually given by the ratio of amplitude of the reference wave to that of the carrier wave, and this is nothing but modulation index. And here output RMS voltage, it completely depends upon the width of the pulses, and these widths depend upon the modulation index. So here, if we are controlling the modulation index, we are actually controlling the output voltage of the inverter. And here in sinusoidal PWM technique, here your V0 RMS is given by the formula. V0 RMS is given by the formula Vs sigma m is equal to 1 to P delta m by pi is nothing but your V0 RMS of sinusoidal pulse width modulation technique. And here sinusoidal pulse width modulation technique eliminates all the harmonics which are less to that of 2p minus 1. And for example, let us consider the number of pulses as P is equal to 3. In that case, this equation becomes 2 into 3 minus 1, which is 6 minus 1 is equal to 5. That means the lowest harmonic which is actually present in the system is only fifth harmonic. And the harmonics less than that of the fifth harmonic, like second harmonic, third harmonic, and fourth harmonic, will be absent in the system. So that is the advantage of this particular sinusoidal or pulse width modulation technique. Why am I calling it as an advantage? See here, harmonics are unnecessary thing, and that is, the harmonic is nothing but the distortion of the waveform, actual sinusoidal waveform. Distortion from the actual sinusoidal waveform is nothing but harmonics, and because of these harmonics, it induces losses into the system, and at the same time heating will be increased, and which ultimately reduces the efficiency of the system. Thereby, the harmonics need to be eliminated. So, by making use of sinusoidal pulse width modulation technique, here switching losses will be less, and at the same time harmonics will also be reduced, which is very essential. Thus, it is desirable to use more number of pulses to eliminate harmonics. But if you see, if more number of pulses, in the sense switching losses will also get increased. Hence, the optimal value of the pulses should be selected such that the switching losses will be reduced. At the same time, harmonics will be kept at check. So that is the thing. And then coming to the modified sinusoidal pulse width modulation technique. Here in modified sinusoidal pulse width modulation technique, if you see, there is a sine wave which is actually compared with the carrier wave. This is just similar to that of the sinusoidal pulse width modulation technique. And if you ask me, what is the difference between sinusoidal pulse width modulation technique and this modified sinusoidal pulse width modulation technique, is plus or minus 60 of this particular sinusoidal waveform, the triangular carrier wave will be absent. And this carrier wave is present from 0 to 60 of the sinusoidal waveform, and at the same time from 120 to 180 of the sinusoidal waveform. And in this mid path, the carrier wave will be absent. That means we are actually going for the optimum number of pulses for the transistors, such that the idea is switching losses will be reduced and thereby efficiency can be increased. And at the same time, control will also not be so complex. So that is the idea behind. And you know very well, this is nothing but the sine wave is nothing but the reference wave, and this reference wave is actually compared with the carrier wave. And as you all know by this time, this is the amplitude of the carrier wave, and frequency of the carrier wave is denoted with Fc, whereas sinusoidal waveform amplitude is actually denoted with Vr, and the frequency is denoted with Fr. And here, when the sine wave is actually compared with the carrier wave, the resultant pulses will be nothing but, it will be acting as a base drive for the transistors of the inverters. So, this is the base drive of the transistor 1 and 2. And this is the comparison of another second sinusoidal waveform with the carrier results in the pulses which are actually required for the transistor 3 and 4. This will now act as a base drive for the transistor 3 and 4, such that these will be triggering the transistors respectively, and which gives in the resultant controlled pulse width modulated inverter output. And this is the inverter output with magnitude Vs, and these transistors will be triggered accordingly. And this is nothing but the output voltage of the respective inverter. And as I already told you, width of the pulses near the peak of sine wave do not change much when modulation index is changed. If you see here at the peak of the sinusoidal waveform, the sine wave does not change much because carrier we are not providing over here, and here carrier is suppressed at plus or minus 30 in the neighborhood of peak of sine wave. And here triangular wave is present for the periods of first 60 and last 60 of the half cycle, for the first 60 as well as last 60 of the half cycle. And here middle 60 does not have any triangular wave, and hence generated pulse width modulation have less number of pulses, and thereby switching losses can be reduced, and at the same time harmonics can also be reduced. And here RMS value is more for same number of modulation index. And this scheme reduces switching losses, as I already told you, and implementation of this system is complex when compared to that of sinusoidal pulse width modulation technique. That is the only disadvantage associated with this particular scheme. The only thing is here we cannot provide we are not providing any carrier wave in this particular part of the sinusoidal waveform. At the peak of the sinusoidal waveform, since we are not providing any carrier wave, the control will be a bit complex when compared to that of sinusoidal pulse width modulation technique. And if you ask me, sinusoidal pulse width modulation technique is the most widely used technique when compared to any other pulse width modulation technique. And here, phase displacement technique. Here, this is the output voltage of the inverter 1, and this is the output voltage of inverter 2. And if you see, the output two inverters are connected in parallel, and output of one inverter is phase shifted with respect to another inverter by a phase displacement of beta. So net output depends on phase shift between two inverter outputs. And here output of the inverter 2 is phase shifted with respect to inverter 1 by beta. So the final output will be V0 is equal to, it is given by the formula V01 minus V0, and this is nothing but the final output of the inverter. So here we are making use of two inverters which are connected in parallel, and the output of the inverter 2 is phase shifted by output of inverter 1 by the phase displacement of beta, and resultant is the output voltage which is given by the formula V0 is equal to V01 minus V0. And then let us check out the output RMS value. And here it is given by the general formula V0 RMS is equal to, general formula is 1 by t, 0 to t, V0 square of omega t d omega t whole to the power of 1 by 2, where here time period is taken as pi, and it is actually conducting from 0 to beta, V0 v square omega t d omega t whole to the power of 1 by 2, where v is taken out and this is v square by pi, and beta minus 0 is beta upper limit minus lower limit, and this whole to the power of 1 by 2. In that case we get v root over beta by pi. This is nothing but V0 RMS, whereas output voltage of another inverter, that is denoted by V01 RMS, and it is given by the formula 2 root 2 Vs root over beta by 2. And this is another phase control, that is phase displacement technique. And let us solve a problem based on this phase displacement control. Considering a single phase bridge inverter, consider phase displacement method of output voltage control. If DC voltage is 200 volts and required RMS fundamental output voltage is 90 volts, determine the delay angle beta he is asking. So here DC voltage, it is Vs is equal to VDC, DC voltage is equal to 200 volts, and the other thing which has given is output voltage, where V0 is equal to 90 volts. He is asking us to determine beta, And since he is asking us to consider this phase displacement control, the output of the inverter is given by V naught RMS is equal to 2 root 2 Vs root over beta by 2. And here V naught RMS, it is given by 90 volts. Since V naught RMS, it is given by 90 volts in the question, let us substitute 90 to root 2, where Vs is nothing but the supply voltage, which is given by 200 root over beta by 2. In that case, if we dissolve, we'll get beta is equal to 18.3 degrees. This is the angle which is required in order to obtain the required output voltage of an inverter. Thank you.